What is a matrix aside from a movie series that have lots of plot holes? A matrix in mathematics is just a collection of objects. In simplest term, it's a collection of things. Now, since obviously we're talking about math, those objects tend to be numbers, but technically you could fill a matrix with colors, you can fill a matrix with animals, any noun or any object you want, but we typically fill them with numbers. So a formal definition, a matrix is a rectangular arrangement of numbers. Right? I mean, again, it could be anything, but since we're interested in math, we'll do numbers. Placed in rows and columns. So for example, I'm just going to make up a random matrix. There's nothing special about these numbers. I'm literally just making them up. Matrices always have a name, usually capital letter, equals, and we typically use square brackets to denote matrices. So I'm pretty lazy. 1, 2, 3, 4, 5, 6. That is an example of a matrix, right? The exception to the rule is typically when you get into higher mathematics, pre-calculus, calculus, and beyond, sometimes they'll use open parentheses for matrices. Right. It just depends on the style. It depends on the professor. So the closed brackets, the square brackets are the standard, but the open parentheses are also acceptable as well. So the vocab word in matrices we call the dimensions of a matrix is the number of columns, or excuse me, number of rows by number of columns, right? And I sort of made a little flub there. I accidentally said columns first, but it really should be number of rows by the number of columns. In matrices, order matters, right? So there's a difference between a 3 by 2 and a 2 by 3. Let's use our same example, my non-clever example, 1, 2, 3, 4, 5, 6. We can see that it has 2 rows. We should be able to see it has 3 columns. So rows are horizontal, columns are vertical. So we would say that matrix A is a 2 by 3 matrix. It's always rows first, columns second. You guys okay with that idea? Yeah. Every number inside of a matrix has a location or a position. The position of an element inside a matrix is designated by its, not surprising, row first, column second. Row number, comma, column number. For example, let's take a look at an example matrix. Again, let's take a look at my non-clever example. Matrix A, 1, 2, 3, 4, 5, 6. Let's analyze one of the elements. Let's say number 6. Right. Can we agree that number 6 is in the bottom row and the last column? This number 6 here? He's in the bottom row, last column, or if I were to use numbers, he's in the second row and third column. We see that the element 6 is in row 2, column 3. Therefore, we write, if you want to talk about specific elements, you use a lowercase letter. So matrices, they get capital letters. The individual numbers get lowercase letters. So since this is matrix A, I would say lowercase a. He was in row 2, column 3, right? So I'd say little a, subscript 2, comma 3. So that 2, comma 3 is a small subscript, is 6. Are we okay with this notation here? This literally says the element in matrix A in row 2, column 3 is 6. That's how you read that notation. Okay? Now, like I said, we're going to do more advanced stuff with matrices later in the week. Today, I just want to stick with the basic operations. Just get a feel for matrices, get our feet wet. So we're only going to do the basic arithmetic operations, adding, subtracting, scale and multiplication, and solving basic equations. We'll solve more advanced equations later. Right. So let's talk about adding and subtracting matrices. Since matrices are nothing more than a collection of numbers, adding and subtracting should follow the same rules as adding and subtracting regular numbers, and that's indeed the idea. To add or subtract matrices, you simply perform the operation on the corresponding elements. What do I mean by corresponding? I mean you do top left with top left. You do top middle with top middle. You do top right with top right. You do not mix and match. To add and subtract, you literally just add and subtract the corresponding pieces. Let's do an example here. Again, I'm not very clever. Say 1, 2, 3, 4. And let's subtract 5, 6, 7, 8. So corresponding elements. Top left corresponds with top left. Top right corresponds with top right. Bottom left corresponds with bottom left. Bottom right corresponds with bottom right. So you just don't look at the big picture, look at them individually, and then just do the subtraction. Yellow minus yellow is -4. Blue minus blue is -4. Orange minus orange is -4. Pink minus pink is -4. That would be the answer to that question. No, not at all. Because I wasn't clever, it ended up being that way. Let me, since these are notes and they're all answers -4, that's not very helpful. I'll show my work here. So this is 1 minus 5, 2 minus 6, 3 minus 7, 4 minus 8. So that's what gives us the -4, -4, -4, -4. Yeah.
Do we have to show that?
No, not at all. I'm only showing it for our notes because, it's notes. You can just go straight from here to here. Yeah. You guys understand adding is the same way? So I'm not going to do that. Do note, the idea says you add or subtract the corresponding elements, which means we need to have a corresponding element. So, big idea. Adding and subtracting matrices only works when the dimensions are the same. A natural question to any absolute statement. Adding and subtracting only works if the dimensions are the same. Natural question would be asked, well, okay, Mr. Vo, well, what happens if they're not the same? Well, if they're not the same, then you just simply say it's not possible. So, for example, if I asked you to do something like, 2, 3, 1, 0, 8, 9, and I want you to add it to 1, 2, 3, 4, 5, 6, let's practice our dimensions. Dimensions are rows per column. What's the dimensions of the first matrix? 2 by 3. Dimensions of the second matrix? 3 by 2. They are not 100% the same, so I would simply say not possible. Okay. You guys okay with that? All right. Like I said, we're only going to do the basic stuff today, so this should be fairly quick, simple, and straightforward. What other things can we do with matrices? We can do something called scalar multiplication. That sounds fancy, doesn't it? Scalar multiplication. Do you know what that really means?
No.
That means distributive property. The reason why they call it scalar multiplication is because the distributive property is multiplication. And then what you're doing is you're scaling the matrix. So if I multiply by 2, you doubled it, you scaled it by 2. If I multiply by 3, you scaled it, you tripled it. So, it's just, it sounds nicer, scalar multiplication. So here's the idea. For any real number, C, and any matrix A, C times A has you multiplying every element in A by C. For example, if I had -3 times 2, 5, -1, 0, all that tells you to do is take every single number on the inside and multiply by -3. So this is -3 times 2, -3 times 5, -3 times -1, -3 times 0. And of course, that gives you -6, -15, +3, and 0. I'm only showing the middle step just because it's our notes. I totally expect you to go from the problem straight to the answer. You don't have to show the middle step if you don't want to. I hope that's also straightforward. Right. The last thing we can do with matrices is actually use them in equations. If they're nothing more than collection of numbers, they should play the same roles as regular numbers do in an equation. So you can put them in front of variables, you can put them within variables, so on and so forth. To solve matrix equations, we have to understand one property, and that's the property of equality. So the property of equality of matrices state two matrices are equal if and only if their corresponding elements are equal. What that means is, if I claim matrix A, B, C, D is equal to matrix EFGH. If I claim this, the only way that that's possible is if A equals E, B equals F, C equals G, and D equals H. Top left equals top left, top right equals top right, so on and so forth. So claiming that a matrix, or claiming that two matrices are equal, is a very powerful statement. You are saying, I will bet money that the corresponding pieces are the same. We can exploit this property of equality to solve basic matrix equations. For example, suppose I ask you to solve this equation. It's going to look very messy and ugly, but I promise you, it's just adding, subtracting, and multiplying. Suppose I ask you to solve 3 times the quantity matrix 5x minus 2, 6 minus 4. Sorry, I said minus. They should be negative. Plus matrix 3, 7, negative 5, negative y. Close the parentheses, equals matrix negative 21, 15, 3, negative 24. Right. That's a funky looking equation, but it is an equation nonetheless. It just so happens to be a matrix equation. These are basic equations because the variables are on the inside. Later this week, we'll take a look at the advanced matrix equations when I pull the variables on the outside. But for this one, the idea is simple. We're going to exploit the property of equality by making sure that this statement says one matrix equals one matrix. So what you want to do is simplify both sides. Now, the right-hand side is already simplified. It's already one matrix. So what we're going to do is we're going to perform operations on the left side to condense it down, right? So you can, regular algebra, you can distribute first, or you can do the parentheses first. It really doesn't matter. I think I'm going to distribute first. So the first step I'm going to do is distribute the 3 into the matrix. So that gives me 15x, negative 6, 18, negative 12, plus 9, 21, negative 15, negative 3y. I didn't do anything to the right-hand side, so I just copy them down. Next, what we're going to do is we're going to add these two matrices. And again, to add or subtract matrices, you only do it to the corresponding pieces. So top left plus top left, top right plus top right, so on and so forth. Now, if I do top left plus top left, 15x plus 9, I can't do that. They're not like terms. So if they're not like terms, we'll just keep them separate. 15x plus 9 is just 15x plus 9, right? Let's do top right. Negative 6 plus 21 is 15. Let's do the bottom left. 18 plus negative 15 is 3. Let's do the bottom right. Negative 12 plus negative 3y. They're not like terms, so you just leave them separate. So now notice the sentence that we have. The left matrix equals the right matrix. So we employ the property of equality. That means top left equals top left, top right equals top right, bottom left equals bottom left, bottom right equals bottom right. Do you see here how the blue and the orange, they're sort of like no duh? Let's take a look at the blue, the top right. We get 15 equals 15. Of course that's true. Bottom left, the orange, 3 equals 3. Of course that is true. So if our goal is to solve for x and y, do you agree that I only care about the top left and the bottom right? We only care about the yellow and the pink. So when it comes to writing out the equations, you don't need to write 15 equals 15. That's useless. Go ahead and write out 15x plus 9 equals negative 21, and then negative 12 minus 3y equals negative 24. What do you know? It gives us two smaller equations, two easier equations, I hope, to allow us to solve. So we're home free. Just solve for x and y, and we're done. Let's work the left equation. Let's subtract 9 from both sides. What is that? 30, and then divide both sides by 15. X equals negative 2. Let's solve for y in the right equation. Let's add 12 to both sides. That's going to be negative 12. And then divide out the negative 3. Get a positive 4. Yep. Easy peasy. We solved that equation.
So would it be negative 2 minus negative 21?
Negative 2 minus 20. Which one are you looking at?
The yellow.
The yellow. Oh, so it's not quite. So it's not going to be negative 2 minus 21. What this sentence here says is that the yellows are equal. So that's why I wrote 15x plus 9 is equal to negative 21. Yeah. That's it. Any other questions with this example?
Do we have to graph these two?
No, there's no graphing in this section. Yeah. So, I mean, there's a lot more we can do with matrices, and we're just going to take it slow and steady. So today we're only going to do the basic operations. By the end of today, I expect you guys to be able to add matrices, subtract matrices, scalar multiply them, and solve basic equations. That is 3-7.